a local decision. Let me give you an example with this function. And that's something that I already posted on Piazza. In order to maintain, okay, so the implementation that I have here is not collective because everybody but the guy with the token will be stuck in that function forever, okay? So the function is not collective in that sense, okay? How can we make it collective? Well, taking in account that the function is supposed to be collective, okay? There are basically three types of behavior that a process can have. First, I have the token. So I have the token. My goal is now to move the token to the next process. So I will issue a send. Good. But then the other side is not, I don't have the token, I wait for a token. No. Is, am I supposed to receive the token this time? If yes, then I will post a receive. If no, then I will not post a receive and I will basically do nothing because it's not my turn. But I participated into that call, okay? Allowing everybody to know that I've been here X number of times so that every process can reason on that number. Because if you know that locally you call this function 6 times, you also know that globally all the processes call that function 6 times, right? At least 6 times, because it's not necessarily blocking, it's not necessarily blockingly collective, it's just collective, okay? So it allows you by a simple local counter in that function to reason about the global behavior of the scale of your entire application. And that also explains why this implementation doesn't work, okay? Why? Well, and that's what the bot is doing. One of the things that the bot is doing is making sure that your functions behave as a collective function, which basically means that if after each call to take a next, I put an API barrier, your application should still correctly work, okay? So if the application, so we'll talk again about this code. So let me save it for a while in case I need to come back to it, okay? Here is how I debug applications, okay? When I try to understand what's going on in my application, well, obviously the first thing is to find the smallest example that breaks, so such that you don't have to think about 1,000 processes, you have to think about a very small number of processes. In this particular example, I can start with 3 processes, and it will be, you will see very quickly why that particular implementation of the function is not correct. So let's take 3 processes: process 0, process 1, process 2, okay? Well, there are a lot of variables inside and they will do a lot of things. What I'm interested in is to know who owned the token, okay? So I have a special table here where I will put here the token, the value of the token on each one of these processes. And as I go through my implementation, I will change this value here locally on each one of the process, okay, to reflect the behavior on the application. So we said in the beginning, the homework says in the beginning that you start with process 0 owning the token, okay? So the process 0 has the token set to 1, and then everybody else has the token set to 0. We good? Okay. And I will talk specifically about the implementation that I just put on the previous slide, okay? And I will imagine a bot that will basically do that validation of a collective behavior. So it will call in a loop, take a next, followed by MPI barrier on the same communicator, obviously, right? Okay, so that's what my bot will be doing. Okay, so take a next, remember the implementation. If I own the token, I do a send. If I don't own the token, I do a receive. Good. So what will happen here? Well, let's see what process 0 is doing. Process 0 goes in that tconnect function and say, do I own the token? Yes. What I'm supposed to do? I'm doing a send to process 1. That's a blocking send, okay? Good. Because the blocking send means that I'm stuck in the send until the data, I can modify my buffer, which means the other guy has received the data. Let's take that assumption, okay? Good. So that process now it's blocked. Process 0 is blocked somewhere in the middle of tconnect function. Okay. Let's imagine process 1. What process 1 does? Goes in that function, in tconnect, and say, do I own the token? No, then I post the receive. Okay, so he posts the receive. Excellent, because that receive will now match with the send on the other side and will allow the process 0 to continue. So I mark that there's a continuation of that process. It's not blocked anymore. But let's reason on what's going on with process 1. Well, the receive was matched, so process 1 will also continue out of that receive. Moreover, not only he receives the token, but he will change the value of token. So that token from 0 will now become 1. Okay, I don't modify P0 yet, but I will get there. Okay, so now the value of token in process 1 is 1. Excellent. What is this process doing? Well, it's going in the barrier. Okay, whoops. It's going in the barrier. The good thing with the barrier is that a very strong synchronization, nobody will go out until everybody completes. So that process is now stuck into that barrier. Let's go back and revisit what process 0 is now doing. So because of that implementation and the fact that there was a receive matching with the send, process 0 will get out of the send, and what he does before leaving that function, it sets the local token to 0. He doesn't have the token anymore. He delegated the token to process 1. Okay, so he's coming back of tk next. What is he doing? He's going into the barrier. Not the right color. He's going into the barrier. Okay, so far so good. 2 of my processes are now in the barrier. So it looks as they, at least these 2, they behave in a very collective way, because there was a call to tconnect, they did whatever was supposed to do, and then they move over. Now let's imagine what will happen with process 2. Process 2 goes in tconnect, and his token is 0. So what does he do? That function say, if the token is 0, the implementation that I just showed, say, if your token is 0, you post a receive. Okay. Now, that receive will never complete. Why? Because the send that is supposed to be matched with that receive will happen in process 1. I know it because he's the one that must give me the token. But before the process 1 gets to that send, he needs to finish the barrier. Okay, and the barrier being a very strong synchronization, I need all the processes to reach the barrier before I can get out of there. So because process 2 is now stuck in that receive, he will never join the others in the barrier. Therefore, we reach a deadlock. Everybody's stuck in a different piece of code, and there is absolutely no way for these processes to move forward. Okay, so clearly, my function tconnect does not have a collective behavior. So, questions? Oh, you must have questions. There are 15 people that didn't succeed on that exercise, so you must have questions.
So the code that's calling the tk-next function is implementing the barrier. Is that how the function's used?
Well, it turns out that a part of the bot, one of the tests, it does call a barrier, yes, but it's not the problem of the bot or of the validator, is the fact that because the homework asks you to implement a function that has a collective behavior, working with the barrier inside should lead to a correct application. And what I'm just showing you here is that when I put the barrier, that previous implementation is not collective. Let's make it simple. Let's take another step here. Let's imagine exactly the same application, but I remove the barrier. Okay, so I still have P0, P1, P2. I have my token here. The token is here. There is no token here, no token there. And now what my application is doing a loop around TK next. Okay, good. So let's run this application. Let's imagine we are process 0. Okay, we go in TK next. The token is 1. What do? We post a send. Okay, and we now block because it's a blocking send. We cannot advance until that receive was posted. Good. So let's move in process 1 and imagine what process 1 will be doing. So process 1. So let me mark the iteration here. Okay, the iteration being this, the loop iteration. Process 0, it's at iteration 0. Okay, good. That's it. Process 1 now, let's imagine what process 1 is doing. He's also at iteration 0. He goes in the loop and he say TK next, I don't have a token, I post a receive. Okay, good thing. This will match together. Okay, so process 1 gets out of the TK next, and it's in the loop. It goes back into the loop. He puts his token to 1 because now he owns the token. Let me not put it there. Let me put it here, up there. Okay, so now the token is 1 on process 1. Okay, and he's in the loop. He finished the loop. He goes back in the loop. He calls TK next again. Now the token is, there is nothing that blocks me, right? So I can just continue doing that in process 1. So he has a token, he posts a send. But now he's in iteration 1, right? Not 0 anymore. Okay, and send, it's a blocking operation, so that process is now stuck. Let's go and simulate what happened in process 2. Process 2 goes in the loop. He doesn't have the token. He's calling a receive. Well, it turns out that luckily the send has been posted there. Okay, so that send now matches, which basically means that this process is out of the blocking send. But now we're talking about process 2. So the receive match, he changed the token to 1. His iteration was 0. He goes out of the TK next. He goes into the loop. He changed the loop to 1. He has the token, right? Yes. So now he's going back into the next iteration because he's iteration 1 and he's doing the send. Okay. And now he's stuck because there's no receive on the other side. So he's stuck in the receive, in the send with iteration 1. Let's go back to process 1. Okay. There was a matching receive. So the process 1 is out of the blocking send. He sent the token. So now he put his token to 0 because he doesn't have a token anymore. Okay. He's going out of the TK next. He's back in the loop. He will increase the loop size, the loop iteration, which was 1, he will put it to 2, right? And he's going back in TK next. He doesn't have the token, so he is posting a receive. And now he's blocked there, okay? Because there's no send that will match this receive yet. Okay. Let's continue. What about process one? Well, process one was kicked out by the fact that the process zero, sorry, was out of the blocking send because process one posted the corresponding receive. So he is now out of there. He will mark his token as being 0 because he sent it, so he doesn't own the token anymore. He's out of TK next, right? He's increasing the iteration to 1, okay? And then he goes back into TK next with token being 0, so he posts a receive. And now he's blocked into that receive. Good thing is that, look, I have a send here. I have the send that match this receive, okay? So he's out of the receive. He now has the token. He put back the token to 0. He's out of TK next. He changed the number of his iteration. He's iteration 2. And he has the token, so he's going back to the send, okay? Good thing here, that send already has a posted receive, okay? So we talked in the beginning about the fact that these are all independent processes, okay? The only moment where you can reason about what's happening is when a process is doing something blocking, okay? So that's why every time I take a process until I hit a blocking point, which is a send, a blocking send, or a blocking receive, okay? That's where my processes will stop. But I can imagine any sequence of a process being run or not. I'm just picking one here, okay? It doesn't mean that that's the only one that is valid, okay? Any order of execution between the processes will be legit, except to cross a blocking operation without a match on the other side. So that won't do it, okay? But other than that, it's fine. So I can continue here with process 0 because the receive was posted on process 1. So I will mark this process as being out of the receive. And I can continue with my process 0. So he managed to send. He now is putting the token to 0. He's out of TK next. He's going to the next iteration. Now his iteration is 3, okay? So what does he do in iteration 3? He goes back to TK next, okay? But with token equal to 0. So he will now post a receive, okay? Again, receive, blocking, we're stuck in there until the send is done. So the thing here is that this seems to work, right? You see the token is moving around. There is no issue here, but you cannot reason on any global behavior from any point of view of a single process, because look at this scheme, okay? It can happen that I have a process that is at iteration 3, that process is at iteration 2, and this process is still at iteration 1. Totally possible, okay? Because they never really had a global synchronization. So the problem here is that not having that barrier basically gives them so much freedom that they can do whatever they want and get totally out of sync. And that's why you understand that they are not behaving collectively here. Here is as if each one of this process was being selfish, just looking at what I am supposed to do and not trying to help the user, the developer, have any global view. You cannot reason on the state of a particular process to know what is the state of the global work. That's basically the thing when you miss that collective behavior. Thing that I can do if I go back, well, if I change the implementation, okay? So that's why it's as soon as I put that barrier there to really enforce the collective behavior, that code, this particular code here, deadlocks. Okay, is that more clear now?
Yeah, no, I get what you're saying. So the key is that at the end of each round of processes, all the different processes agree on who has the token, right?
Exactly. Yes.
Okay.
And that allows you as a user to reason of a collective behavior of the algorithm. Okay.
Right.
You don't necessarily know exactly where the other processes are. That would be difficult. Okay. That's basically force you to put barriers all over the place. That's not the point. The point is that you know that they have been reaching a certain point in the execution because this function is collective.
Okay.
Okay.
Right. And it doesn't really matter how you implement that in the code that runs the method. It just matters that our method is able to act collectively.
Exactly. And
Thanks so
this
much.
simple code, you see, that's a very simple way to enforce the collective behavior of anything. It's put a barrier. I'm not saying that it's useful. No, it's not, because if the function was correctly collective, then that barrier will have no sense. Okay, it would have been just pure overhead, but it highlighted an incorrect implementation that would have worked in an application without that barrier. Okay, so this implementation is partially correct. Okay, yes, it's moving a token around, yes, but not in a collective way. Okay, and again, really, the point is not to put burden on implementing this function. Is that you need, in many cases, you do need to be able to reason at a global scale. So you need this collective behavior to be exposed one way or another, because that will allow, that simply allows you to know where everybody is, more or less, logically at least, which stage of an algorithm they have reached. Yeah. And that's also the usage of a barrier. Okay, the barrier is a very strong synchronization that basically tells you, hey, everybody reach at least that point. Good. I now know that we can all happily move to the second stage or whatever you're doing in your algorithm. But you reason globally by simple local information, and that's exactly the goal of this TKN.
I'd say that's why.
All in all,
That's why you have to get a receive from the person behind you to see if you.
I have the token, I send the token.
To see if you have to get a receive from the person behind you to see if they send you a 1 or a 0.
With the collective behavior.
And so because of that, I feel like our implementation is just as efficient, because if you have to receive from the person behind you and then conditionally get the buffer, then I feel like you might as well just do it.
I feel like a two-way communication doesn't incur a lot of costs.
Bruh.
Oh, I got it. I was about to push the button. Is that gonna work? I don't think so. Did you play it? Oh, whatever. Oh, if you need to use your laptop and the situation doesn't work for you.
There will be a little bit out of sync between
Oh.
okay? That is inherent to the distributed application. But yeah, the only way to keep everybody in sync all the time is to sprinkle and play barriers. But then you're losing all potential performance benefit, because it's a very strong synchronization. So we don't necessarily want to do that, but we do want to be able to reason globally about this thing. Okay. So that's good that everybody is processing to it, because now you will remember this. Hopefully
We do not.
See
Oh, we can
that
pull
will
it in.
facilitate the next homework, which will basically be to implement a communication scheme in that Jacobi, in the Jacobi or Laplace or whatever you want to call it, in that scheme where across a bunch of data to do an update on the operation, and you will implement processes will need to talk with two neighbors, or three neighbors, or four neighbors.
So maybe we could add an if statement, which is if
So what
you
will do
have the
from
token,
now on over the next few hours, there will be more often
or
now
if
that
you-
got a little bit
if you
familiar,
have the token,
see all this-
send the
all
buffer.
the issues
If you
here.
get the token, receive the
Is
buffer.
that we'll take this Jacobi. Okay, I will give you a
Does
framework.
that make sense?
So that
Yeah,
you
I guess,
don't have to write in my function. Nobody cares about that. Okay?
I guess at first when I started the problem, I was confused by what was actually in the token
How we
buffer.
can implement
Yeah.
the
Um,
communication buffer.
Like,
And you will have to take it from. You have
So
to
I guess-
implement it with blocking.
I guess I was like confused about how it's
And
being
then
called.
no
But
blocking
what I
the
understand
system,
is that
blah, blah, blah,
that
one
function's going to be called
everything.
for
We'll do the whole spectrum so that you see how you can implement exactly
However
the
many,
same algorithm with all the
whatever
capabilities of
processes
of
needed,
Android.
right?
Two-sided, one-sided, and never just collected if we have, well, hopefully we have time for that. Okay, so, 30, good. I have some time to talk about, but except if you have more questions.
Worst
Actually, I have a question. Can you talk a little bit more about
scenario.
that you were talking about in order to make sure that
Oh, or
the process that's receiving is indeed receiving and not just being deadlocked?
Well, okay. I can talk a little bit about it, but so imagine that I'm doing. Let's write this function just slightly differently. Okay, so let's say pk next algorithm, whatever arguments they were, and here the token. Okay, and let's imagine that I put inside. I put inside a static int count equals 0. Okay, or actually let's not call it count. Let's call it what it is. It really indicates is owner, the owner of the token. Okay, and because the homework say the token started process 0, I will put 0 as here. Okay, so on every single call to this function, because the function must behave collectively, I know that everybody else, every other process will do the same as I do. We have a call to this function independent of what they are, their involvement, what they are supposed to do inside. Okay, so I can reason at each call where the token will be. Okay, because let's say I process 100. Okay, I'm P100. When my owner will be 50, that basically means that I have been called, or I call this function 50 times. Good, because I increase it every time I use this function. Okay. So that tells me a local information. I've been here 50 times, but it also tells me a global information. Okay. Because everybody had to call that function 50 times. Maybe they are a little bit out of sync, right? But that's okay. They will have to do that function. At the 50th step, the token will move from process 50 to process 51. Okay? And because my rank is 100, I know it's not my time to receive it. So I know exactly that my job here is just to fall through this function to maintain the collective behavior, but neither send nor receive.
Which is not something I just.
Okay?
At first, I
When
forgot
will
about
be
that
my
whole
time to
process
send it?
thing.
Well,
thought
I
that
think that
it was
P100,
one point or
my
two above.
time will be
Right.
when my
So that's where I was confused at first. At first, I didn't even play with the
owner
buffer.
equals 100. That's when I'm the guy on the receiver side. Okay? Or maybe 99 actually. Because then I know that the token is on the guy right in front of me, number 99, so it's not 100 here, it's 99. Okay? So the next one is me. So when the owner is 99, then I would post the entire receipt. Because that's the stage when I need to receive that token. Okay?
CVN is declared inside TKNet.
Sure. Yeah.
So you can increment it, but when TKNet is called, it wouldn't be overriding it.
No, it's a static, so you will do something in the function, you will do something owner plus plus, right? To increment it all the time. But the fact that it's static, it guarantees that there is a single one, and nobody outside this function can access it. So it's some kind of, see it as a private variable TKNet.
Okay, I see.
A private global variable, because it,
Okay, thank you.
His face just remains to stare at me.
yes, so that
What?
counter, that ownership counter allows you to know exactly where the token is at any call in this TKNet function.
Should have got champagne and we could have had mimosas.
Anything else?
Oh, fuck. You're right.
Could have been just like classic.
No?
Like,
Okay. Then let's talk a little bit about OpenSHMEM. So we're moving a little bit away from MPI, but you will see not
OpenSHMEM
necessarily
sounds
very
like
far
a-
because most of the
like a
the concepts
Jewish public
are
outreach
similar.
festival.
You need to move data between two
Everybody, we're having
processes.
OpenSHMEM,
And
feel
we
free
already
to
saw with
join.
MPI that you can do it one-sided and two-sided. Okay.
Okay.
And you saw that the using the two-sided gives you this reasoning about consistency or stages of the where the processes are. And when you use one-sided, you have a little bit less because the puts and the gets, all this operation do not necessarily inform the other side of the operation. So the only moment where you can reason globally about the one-sided is basically when you close the epoch, which is an operation that is a little bit more I'd say collective than the other. Anyway, so that's how MPI provided one-sided. They are gazillion other ways to provide that one-sided. Okay, one of them being OpenSHMEM. And again, this is a user-facing programming model. Okay, if you go below that, you will notice that there are totally different protocols that are maybe a little bit lower level for most of the users, and that's why building the higher level.
If you need your laptop to be independent of the cable, you can also stream you can cast your stream.
To the user. But all those high-level things are built on basically the same low-level information. What do you need? You need something that is called an app. Are built on basically the same. You're sending a very small very small message to another process, such that you inform him about.
Come in and trashed it, but honestly, this is like one of the most beautiful ways to end our adventure. Just like with the overlook of the city, it's just, this has been insane.
Now my audio cut out here, but you can really tell I'm into. With the overlook.
Next, relaxing jazz piano radio.
How do I stop sharing my screen?
What is OpenSHMEM? It's what's called a TIGAS. It's a parallel global address space. Okay, it's a lot of words there. Global address space basically means that we have an additional layer. Again, it's a virtualization layer that will make all the process memory look as if it was contiguous together. Okay, so I will come back to this. You will see it's a little bit nicer. It's kind of similar to the window, but it allows you to reason in terms of displacement, local displacement and remote displacement. You will see. There are a bunch of programming paradigms here. There are some that work at the level of library, so basically they will be used as a lower level library by higher level paradigms or by compilers to write that. There are also specialized languages that will totally hide this concept of this global
What is up with that?
this global memory. Okay,
I think it must be
Hidden. It's probably
him.
how to say data distribution. Okay, so let me give you an example. So in MPI, we talk about that, and you did that in the homework. We can say, hey, I have an application, I have a data distribution, an array that is distributed among 3 processes. Okay, so now I must know as the user that if I want to access, let's say each process have 100 elements, okay? If I want to access the element at position 150, I must go to this will be process 1, this 0, 1, and 2. I must go at position 50 on process 1, because that's where the 150 element in a global array exists, is located, okay? So I must compute the location of that as the user, okay? In these languages, Chapel, Titanium, Xtend, I basically declare the array as distributed from the beginning, and the compiler will do that magic translation between an index in the global array location into a memory space process. So instead of having to say, I want to go in process 1 position 50, I will simply say, give me 150. Okay? Give me the element at position 150. And then the compiler will do the translation between 150, which is the relative address, into you should go to process 1 position 50 and get that thing. So from a user perspective, it's way nicer not to have to mess around with it. But it's not necessarily highly efficient because the compiler, again, the compiler doesn't see the entire scope of the application. It will only see the instructions that are issued one after the other. So it will have a hard time agglomerating data transfer at the same time. And if it only does little transfer by little, the compiler cannot benefit from using the bandwidth of the entire bandwidth of the network. So that's why these languages are not necessarily very used. They remain some kind of niche languages that are using highly specialized type of algorithms. As an example, everything that deals with graph processing, as an example, they would fit very well with any of these languages because by design, they require always access to very small amount of data. Basically, who's on the other side of an edge. So it translates very nicely in these kind of languages. In general, if you try to implement anything like the Laplacian equation that we talk about, this will be a significant burden. So that's basically how this PGAS family is used. We will talk about a particular implementation. Maybe the most used of this is a library. Okay, so you have to explicitly put the calls in order to do the data transfer in. So there are pros and cons on using languages and using libraries. I highlighted some of them. It's kind of difficult overall to say which one is the best, but I will say that right now the because the compiler technology are so lagging behind what the user can do, a good programmer can do, people are more inclined to use the library approach than anything else. Okay, so with that, that's a very long introduction. Let's go back and talk a little bit exactly about how this OpenSHMEN looks at the memory. So I say that it's a P-gas, okay? So the parallel global space, which means that each process will have a piece of memory, but every process will look at this as a piece of a larger array, okay? In exactly the same way that I gave that example there, okay? I know how much each one of my coprocessor has, so I know exactly where to go to get elements when I need them. All synchronizations are now left to the user. So you better synchronize in order to make sure that you get the correct data yourself. You cannot rely on the library to do that. So they are constructing the library to synchronize, but you should do the correct synchronization at the right place. And you will see when we have to implement that Jacobi using this, the one-sided, that it requires a little bit of gymnastics in some cases, because the synchronizations are not implicit in the language itself. I have a few slides about how Core and how UPC and Core is doing, but if you're interested, the slides are here. I really want to talk about SHMEN. Okay. OpenSHMEN is the name of the current standard. It started from something called the SHMEN symmetrical hierarchical memory. Symmetrical in the sense that everybody has to allocate exactly the same amount of data, such that you can easily reason about who's having what. And this was put forward by SGI, a company that was building, or actually by Cray, a company that is building HPC computers. It's still building HPC computers, by the way. But long ago, somewhere in the 90s, more or less in the same time as MPI. So I said when I was talking about MPI that there are multiple programming paradigms that were concurrent in the beginning. It turns out that 99% of the parallel programs today are written in MPI because MPI was, because of the two-sided concept, was giving you this facility to reason about the state of more than just a single process with your back. Anyway, that's the history. A few years ago, I would say around 2005, people decided to bring an approach, and they creating an open standardized standard called OpenSHMEN. Okay, and now there is a version online, and you can do and download the documents. More or less the same type of progress as in MPI. Well-defined MPI, very good implementations. You can play with it. Okay. Okay. So everything inside evolves around this concept of parallel global space. Okay. Remote memory access data. You're not synchronizing with anybody. You just go and fetch data from a memory location that you specify using two attributes. One is the target processor, and second is a relative location in his memory, starting with the beginning of your symmetric parallel. I will give an example in a little bit. They use a slightly different terminology than MPI, so there is no notion of rank as an example. Here it's called a processing element. It does have more or less the same meaning as being a process, okay? So there is a very strong equivalent between the notion of rank in MPI and the notion of processing element here, but they use a different name. Very similarly to the MPI one-sided, origin is the processor that performs the call, okay? same story. And then the remote processor is the other one. We also talk about source and target, but source and target has a direction into them. The source is where the data is copied from, and target is where the data is put. So the origin is not necessarily the source. It really depends on the operation that you're doing. As an example, when I do a get, I do a get, so I am the origin of the call, okay? But I will get the data from some other processor, so the source is that other processor, is not me. I am the target of the operation, okay? Okay, so really the main concept here is what's called symmetric variables. Symmetric variables are arrays that every single instance of your parallel process allocates. Okay. What that would be? That would be basically every
we're out of
single
time.
variable that is on the stack. Okay. Or every single variable that you allocate with a specialized call, because that will basically put the memory in a special address. And why is that? Because something that is called ISO addressing. In order for this model to work, everybody has to put the array at the same virtual address, okay, in memory, such that it's easy to compute the relative jump in each one of these processes instead of having to compute it according to a displacement into the memory of the remote process. Okay. So what are symmetric? Basically, every global variable will be symmetric. That's one. And all the dynamically allocated memory that goes through in C the function shmalloc. Okay. Symmetric hierarchical memory allocation. That's basically what it is. So before we end this, let me show you the how the hello world example will look in OpenSHMEM. Okay. Here is my main. I create a variable that is called x, that is a pointer to an array. Okay, so, and I start, there is no MPI init or OpenSHMEM init. Here it's called start PEs. I start 4 PEs. So there will be 4 instances, exactly like what the MPI run will do. There will be 4 instances of this application. Okay. And then I put something into that variable x by allocating a symmetric memory of size of x, which is a pointer. Okay, so I put an element in there. Now, because I'm not using malloc, okay, I'm using shmalloc. That basically guarantees me that every process, again, this is a collective function. Okay. And in fact, it's a little bit stronger than a collective function because it also assumes that the size is the same on all the processes. Okay? Which basically means that if I know, we're going back to the notion of collective. I don't need to know that everybody is doing it because it's guaranteed by the fact that the function is collective. So if malloc is collective, then everybody will allocate an x somewhere in memory, so I can access it, okay? Because again, I know that their address is the same as mine because of that ISO allocation that this function provides. And because of that, I can simply use read or write, and put or get from their memory.
It sounds like a
It can be an array, it can be
word modifier. Like if people say ish at the end of a sentence, like it's small-ish. It sounds like it's like, well, it's memory.
Yeah, I think it's definitely like a pre-curse, like a
basically
prefix.
synchronize
Yeah.
all my processes, more or less the same idea as in MPI Maria.
Schmemfix
Yeah.
situation.
And that
It's
allows me
Aiden's
to basically guarantee that
girlfriend.
now everybody allocates
Girl-
that array, and I can simply
girlfriend.
use
Like
the
it's-
array from now on. That's basically the idea. And then I free the
He
array
went
when I'm
schmishing.
done, and there is no finalized in OpenSHMEM. The finalization
Yeah, let's
is
get out of this
implicit
Schmem
by the fact
Yeah.
that you return from your main function. Okay. And I will stop here for today.
Yeah, I love filler
We'll
words.
continue with this OpenSHMEM primitive a little bit, on Friday,
Just
I
forget
guess.
about this open shit.
And give me an hour, and I will post the homework, the next homework on the website. Okay. So with that, I'm really looking forward to see more green on that homework on the bot answer, because hopefully now that you understand what exactly I mean by this collective behavior, you will be able to revisit your implementation of exercise 1, and you get that bot running without timeouts. Okay. Great. Yeah, so if you have questions, don't hesitate to post on Piazza. It's not necessarily private. Some of you post private, some of you post public. I think that if you think that your question can interest
Free.
other people, don't hesitate to post it public.
Start.
You can post it public.
No,
anonymously
Start already has it.
if you really
Smart.
want.
Smart.
Schmem.
Good then.
Smart.
Um,
No, don't
see you
worry.
all on Friday.